Hi everyone, this is Viraj and we'll discuss the important technologies that's Kafka and Apache Storm. So Kafka is basically a messaging queue and Apache Storm is a framework for distributed real-time computation. So to start with, let me just describe what an Apache Storm is. Apache Storm is a distributed real-time computation system. I repeat, it is a distributed real-time computation system. It's similar to how Hadoop provides a set of general primitives for doing batch processing. Storm provides a set of primitives for doing real-time computation. So if we just compare Hadoop with Storm, Hadoop is meant for batch processing systems, whereas Storm is for real-time computation. Storm is simple and can be used with any programming languages. Now we'll discuss about the rationale of Apache Storm. So the past decade has been a revolution in data processing. MapReduce, Hadoop, and the related technologies have made it possible to store and process data at a scales which were previously unthinkable. Unfortunately, these data processing technologies are not real-time systems, nor are they meant to be. There is no hack that will turn Hadoop into a real-time system. Real-time data processing has a fundamentally different set of requirements than a batch processing system. So there are two different things. Batch processing system and real-time data processing system are fundamentally different. They have different set of requirements. However, real-time data processing at massive scale is becoming more and more of a requirement nowadays for a business. So the lack of Hadoop of real time has become the biggest hole in a data processing ecosystem, and Storm fits that hole perfectly. Before Storm, you will typically have to manually build a network of queues and workers to do the real-time processing. So here the workers will process the messages from the queue, update the databases, send new messages to other queues, and so on. Unfortunately, this approach of manually setting up network of queues and nodes, worker nodes, has a serious limitations. So what are those limitations? I have mentioned it on my slide. Those are three: tedious, brittle, and painful to scale. So let's handle one at a time. So why is manually creating set of network of nodes and queues tedious? It's tedious because you have to spend most of your development time in configuring where to send the messages, deploying the workers, and deploying the intermediate queues. So the real-time processing logic that you care about corresponds to a relatively smaller percentage of your code base, and most of your effort goes in configuring where to send messages and deploying the workers. Right? That's why it's tedious. The next limitation is it's brittle. That is, it's a very little of a fault tolerance, because you yourself are responsible for keeping each worker and queue up. And third, it's painful to scale. When the messages throughput get too high for a single worker or a queue, you need to partition how the data is going to be spread around. So you have to reconfigure the other workers to know the new locations where to send the messages. And this introduces moving parts and pieces here and there, which can definitely fail. So just to summarize, these are the three serious limitations you yourself have to manage the set of nodes and the queues. One is it's tedious, because most of your development time will go in configuring this set of nodes and queues. Second is it's brittle. because it's very less fault tolerance, because each worker and queue have to be up and you are responsible for getting them up or keeping them up. And third is it's painful to scale. So when the message throughput becomes high on a node or a queue, then you have to do the synchronization of where to spread around the extra messages in your cluster, right? So that's why these are the three limitations which were there if you had to manually perform what Apache Storm is doing right now. Hence, the best solution is Apache Storm. Okay, so why is Apache Storm so important? So Storm exposes set of primitives for doing real-time computation. Just like how MapReduce eases writing of parallel batch processing, Storm greatly eases writing of parallel real-time computation. So MapReduce eases writing of parallel batch processing, whereas Storm eases writing of parallel real-time computation. So following are the key properties of Apache Storm. So what are those? First property is it's extremely handles broad set of use cases. Storm can be used for processing messages and updating the databases and lot more. Second is it's scalable. Storm scales to massive numbers of messages per second. Third property is it guarantees that there is no data loss. For a real-time system, you must have strong guarantee about data being processed successfully. So if the system drops data, then it has a very limited use cases for becoming a real-time computation system. Hence, only if there is a framework who can guarantee that every message is going to be processed successfully, only those systems are considered to be reliable for your real-time computation, right? So next property of the Storm is it's extremely robust. Unlike systems like Hadoop, okay, which is difficult to manage, Storm clusters just work perfect. It is an explicit goal of the Storm project to make the user experience of managing the clusters as painless as possible. Okay, so managing Storm clusters is actually a very painless job. The next property is it's fault tolerant. If there are faults during execution of your computation, Storm will intelligently reassign the tasks as necessary. So Storm makes sure that a computation can run forever until you kill it. So this is how it differs from Hadoop. In case of Hadoop, the task eventually completes, whereas in Apache Storm, the computation can run forever until and unless you kill that computation. And the last property of the Storm is it's programming language agnostic. That is, if you have so robust and scalable real-time processing system, it should not be limited to a single platform. So Storm can process the components defined in any language. Okay. So following is the URL of a Storm Starter project. You can just visit that URL and download a Storm Starter project for experimenting. In the upcoming slides, we'll discuss how about setting up the entire dev environment and so on. But for now, this is the URL for you all where you can just visit that and get the source code for you all. So now in this slide, we will discuss the very important concepts in Apache Storm. So the first concept that I have here is topology. What do you mean by a topology? So the logic for your real-time application is packaged into something called Storm topology. I repeat, a logic for your real-time application is packaged into a Storm topology. A Storm topology is analogous to your MapReduce job. One key difference is that a MapReduce job eventually finishes, whereas a topology runs forever. I repeat, MapReduce job eventually finishes, whereas topology runs forever. A topology is basically a graph of nodes. Now, what are those nodes? Spouts and bolts. So we'll discuss shortly what do you mean by a spout and bolt, but for now you can imagine topology is a graph of spouts and bolts that are connected with each other in the form of groupings. Okay, so the next concept is streams. So what is a stream? A stream is an unbounded sequence of tuples that is processed and created in parallel in a distributed fashion. I repeat, a stream is an unbounded sequence of tuples that is processed and created in parallel in a distributed fashion. Streams are defined with a schema, okay, and this schema is made out of different fields. So these streams, what I am talking about, is a set of tuples which have a schema defined, and it has different number of fields. So by default, tuples can contain integers, long, shorts, bytes, and many other primitive data types. You can also define your own serializer classes so that custom types can also be used within tuples. So every stream is giving a unique identifier when it is declared. Okay, so the next concept we have is a spout. I just mentioned to you all that topology is nothing but it's a graph of spouts and bolts which are connected to each other, right? So what is a spout? A spout is a source of streams in a topology. I repeat, a spout is a source of streams in a topology. Generally, spouts will read the tuples from an external source and emit them in the topology. So these spouts can either be reliable or unreliable. A reliable spout is capable of replaying a tuple if it gets failed to be processed by the storm. Okay, a reliable spout is a one which is capable of replaying a tuple if the tuple is failed while getting processed in Apache Storm. Whereas unreliable spout just forgets about the tuple as soon as it is emitted by the spout. So spout can emit more than one streams, and you can declare multiple streams while emitting. So the main method in spout is a method named next tuple. So next tuple is a function, okay, that you need to define. So when we will be discussing the code part of the storm topology, that time I'll give you all examples of how to write next tuple. But for now you can remember that next tuple is just a function which emits new set of tuples into the topology, or it simply returns if there are no tuples to be emitted further. Okay, and spout also has very important other two methods, that is ACK and fail. ACK is to acknowledge that a tuple has been processed successfully, whereas fail is to inform the framework that the tuple processing has been failed. Okay, so the next concept is bolts. All the processing in a topology is done in bolts. So bolt is like a processing engine of your Apache Storm. Bolts can do anything, right from filtering of the tuples, applying some functions on it, aggregation, joins, talking to databases, and lot more. So bolt is a processing engine of your topology. Bolts can do a very simple stream transformations. So for doing complex stream transformations, it often requires multiple steps. So you can define or you can break down the task into subtasks, and for each subtask you can assign one bolt, so that when you divide your complex stream transformation task into set of simple tasks, for each task you can have independent bolts, and you can chain all these bolts together in order to achieve your complex task. Okay, so that is what a bolt is. So the next concept is stream groupings. Okay, so what is stream groupings? As part of defining a topology, we need to specify how these spouts and bolts are connected to each other. Okay, we need to define how the entire tuples are going to flow in an entire topology. So a stream grouping defines how this set of tuples are going to be transferred in a topology. So what are the different stream groupings available? I'll explain to you all this. Okay, so the first is shuffle grouping. In case of shuffle grouping, tuples are randomly distributed across the bolt's task in a way that each bolt is guaranteed to get an equal number of tuples. I repeat, in case of shuffle grouping, tuples are randomly distributed across the bolt's tasks in a way that each bolt is guaranteed to get equal number of tuples. Next is fields grouping. In fields grouping, the stream is partitioned by the fields which are specified in the grouping. For example, if a stream is grouped by user ID field, then tuples with the same user will go to the same task. I repeat, if a stream is grouped by user ID, then the tuples with the same user ID will always go to the same task, and the tuples with different user IDs may go to different tasks. Okay. The next is all grouping. In case of all grouping, the stream is replicated across all the bolts tasks. Okay. So it's like a broadcasting. You are replicating the stream across all the bolts tasks. The next is global grouping. In case of global grouping, entire stream goes to a single one of the bolt's tasks. I repeat, in global grouping, entire stream goes to a single one of the bolt's tasks. It's exactly opposite of all grouping. In all grouping, the stream is replicated across all bolt's tasks. Whereas in global grouping, entire stream goes to a single one of the bolt's tasks. Next is non-grouping. In case of non-grouping, this grouping specifies that you don't care how the stream is grouped. Okay, so in non-grouping, we don't care how the stream is grouped. So Storm will normally push down the bolts with non-groupings to execute them in the same thread as the bolt or spout they are subscribing messages from. Okay, so in non-groupings, Storm will normally push down the bolts with non-groupings to execute them in the same thread as the bolt or a spout they subscribe from. Next is direct grouping. So this is a special kind of a grouping, and over here a stream grouped in direct grouping, producer of the tuple will decide which task of the consumer will receive the tuple. I repeat, over here producer of the tuple will decide which task of the consumer will receive this tuple. So direct groupings can only be declared on the streams which are declared as direct streams. And the next is local or shuffle grouping. So in local or shuffle grouping, the target bolt has one or more tasks in the same worker processes. Then tuples will be shuffled to only those which are in process tasks. So in local or shuffle grouping, if the target bolt has one or more tasks in the same worker process, tuples will be shuffled to those which are in process tasks. So these are the different forms of groupings available. If you want to define your own custom groupings, you can definitely do that by implementing custom stream grouping interface. You have to define your own class implementing from custom stream grouping interface. With that, you can definitely have your own custom groupings. So the next concept is reliability. Storm guarantees that every tuple will be fully processed by the topology. It does this by tracking the tree of tuples which are triggered by every spout tuple and determining when the tree of tuples have been successfully completed. So every topology has a message timeout associated with it. If Storm fails to detect that a spout tuple has been completed within that timeout, then it fills the tuples and replaces it later. Okay, so if the Storm detects that a tuple has been completed within that timeout, okay, if Storm detects that a tuple is failed to complete within that timeout, then it marks that tuple as failed and it replaces it later. So to take advantage of Storm's reliability capabilities, you must tell Storm when the new edges is added in the entire topology so that it can keep itself updated. Okay. So the next concept is tasks. Each spout or a bolt executes the task for the cluster. So each task corresponds to one thread of execution. I repeat, each task corresponds to one thread of execution. And stream groupings define how to send the tuples from one set of tasks to another set of tasks. So we just discussed about different stream groupings, right? So stream groupings is defining how to send the tuples from one set of tasks to another set of tasks. The next concept is workers. Topology execute across one or more worker processes. Topology execute across one or more worker processes. Each worker process is a physical JVM and executes a subset of tasks for the topology. Okay, each worker process executes subset of tasks for the topology. So these are the important key concepts in Apache Storm. Now we will try to understand the parallelism of a Storm topology. What makes a running topology? Worker processes, executors, and tasks. So these are the three important components which make up your running topology. One is set of worker processes, executors, and tasks. Okay. So this diagram that I have shown here is a very simple illustration of how worker processes, executors, and tasks are connected to each other. Okay. So the outermost box that I mentioned here is a worker process. Then this box is an executor, and within the executor I have tasks. Okay. So let's discuss more on this. As I've mentioned here, a machine in a Storm cluster may run one or more worker processes for one or more topologies. I repeat, a machine in a Storm cluster may run one or more worker processes for one or more topologies. So each worker process runs the executors for a specific topology. This is a very important point. You cannot have a single worker process being shared by multiple topologies. Each worker process is disjointly shared by, it is not shared. Each worker process is bound to a single topology. You can run many different topologies, many different worker processes, but each worker process is tightly bound to only one topology. You cannot share a worker process with more than one topology. Okay, so this is a worker process. Now in one worker process you can have one or more executors. As I mentioned here, one or more executors may run within a single worker process. So in this diagram, how many executors do we have? 1, 2 and 3. So in this diagram I have 3 different executors. Okay, so one or more executors may run within a single worker process, with each executor being a thread which is spawned by the worker process. This is very important. Each executor is a thread that is spawned by the worker process. and each executor runs one or more tasks of the same component, which can be Spout or a bolt. Okay, each executor runs one or more tasks of the same component. So in this diagram, this executor is executing two tasks, this executor is executing one task, and this executor is executing one task. So an executor, which is a thread that is spawned by a worker process, so this thread can execute one or more tasks. Okay, and what is a task? Task performs the actual data processing. So this diagram clearly helps us to understand that I have a worker process. Inside worker process, it's spawning the threads, and each thread is a executor, and within a executor I can have one or more tasks. So in this diagram, I have one worker process, I have three executors, and I have four tasks, of which two tasks are in executor number 1, task number 3 is in executor number 2, task number 4 is in executor number 3. Okay, so here there are two tasks and here there are one task each, and I have a single worker process, I have three executors, and I have two tasks in this executor, one task in this executor, one task in this executor. So is conceptually things clear? What is a worker process? What is the executor? What is a task? Task is the actual data processing that's happening. Okay. So now let's discuss how to configure the parallelism in a topology. Okay. So the first thing that we need to decide is how many worker processes we need to have. Okay. So you need to decide how many worker processes you need to create for your topology. Next, you need to decide how many executors or threads do you want to spawn for each component. And next is you need to decide how many tasks you want to perform, okay, per component. I have a very simple example, code example here. So I'll explain to you all what this means. Topology builder is a guy with which we are trying to build a topology. Now in this topology, I need to set bolt. So I have a bolt that I want to create here. Okay. So for a builder, I'm instructing this builder saying, please set me a bolt, okay, whose name is green bolt. So green bolt is like identifier to this bolt. Now I'm instantiating a class called green bolt, which is having a logic of that bolt. Okay. And parameter number 3 is parallelism. So I'm expecting 2 executors for this particular bolt. Okay, so for a green bolt, this green bolt is an identifier. I'm creating a new green bolt instance, and parameter number 3 tells how much threading or parallelism we are expecting here. So parallelism is the number of threads, which is number of executors. So in this example, I'm expecting parallelism to be 2. So I'm expecting 2 executors. Then I'm setting how many tasks I want for this component, and I'm mentioning it as 4. So I want 4 tasks and I want 2 executors. So can you tell me how many tasks one executor will hold? 2, right? Because I have 2 different executors, which this 2 tells me, and I have 4 tasks. So 4 divided by 2 is 2. So one executor will hold 2 tasks. And I am expecting shuffle grouping. What is a shuffle grouping? Shuffle grouping is one in which tuples are randomly distributed across the bolts coming from the input, so that each receiving bolt will receive the messages equally. And I am receiving input messages for this bolt from blue spout. That is, there is a spout whose name is blue spout, which will emit messages to green bolt, and green bolt will receive the messages from the blue spout in shuffle grouping fashion. Okay, So green bolt will receive the messages from blue spout in shuffle grouping fashion. So let me just brush up this part. So I'm creating a bolt here whose identifier is a green bolt, and I'm instantiating a class called green bolt. So your logic of green bolt will reside in this class green bolt. Then I'm expecting parallelism to be 2. That means I'm expecting 2 executors or 2 threads to be active for this component. Then I allocate 4 tasks for this particular bolt. So that means one executor thread will host 2 different tasks of this component. And then I'm saying receive the input messages for this bolt from blue spout and use shuffle grouping. That means the input messages will be equally split and randomly distributed to this particular bolt. Clear? I have a very interesting diagram here which will clear a lot of our concepts. So this diagram shows a simple topology, how it will look in a particular operation. So this is a topology wherein I have 2 different worker processes, and now this worker process, can you tell me how many executors it is having? 1, 2, 3, 4, 5. So I have 5 different executors in this worker process. How many executors this worker process has? 1, 2, 3, 4, 5. So this worker process also has 5 different executors. So how many tasks are there? 1, 2, 3, 4, 5, 6. So 6 tasks in this worker process. What about this? 1, 2, 3, 4, 5, 6. So there are 6 tasks here as well. So this is a simple picture of a topology which is made up of set of worker processes. Each worker process has a set of executors, and each executor is hosting single or multiple tasks. Clear? Then this is a topology diagram that I have. I have a spout here which is a source of streams to my topology. It will take the input from external source and it will emit to a set of bolts in a topology. Now this blue spout is emitting set of messages to green bolt. Green bolt receives the messages, does some processing and emits the result to another bolt, that is yellow bolt. Yellow bolt takes the processed messages from the green bolt, applies some more logic to it, and then places the final output into either the database or a file system. Okay, so this is how the chaining happens. A spout picks the messages from external source and it just emits them to the green bolt. Green bolt will apply the intelligence and it will forward the result to yellow bolt. Yellow bolt will receive that message, it will apply its own intelligence and place the final output either on a file system or a database. Okay, so this is how the entire message flow happens in a topology. Okay, so over here for a blue bolt, I am mentioning that I want parallelism hint to be 2, which is nothing but I want 2 executors or 2 threads. Okay, so that's why you can see for a blue bolt I have 2 different, one here and one here. I have parallelism 2, 1 and 1. For a green bolt I want parallelism hint to be 2. Okay, so there need to be 2 executors for a green. So I have one over here, one over here. So there are 2 executors for green as well. For yellow bolt, I want parallelism to be 6. That means I need 6 executors. 1, 2, 3 over here, 1, 2, 3 over here. So 3 plus 3 is 6. Right? So for yellow bolt, I want 6 executors, which is spread across 2 workers. For green bolt, I want 2 executors, which is spread with 1 worker each. And for blue bolt, I again want 2 executors. Okay, which is 1 and 2. So with this, what is the combined parallelism? 2 plus 2 plus 6, total 10. So there are 10 executors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 different executors. And I have 2 different worker processes. So divided by 2 is 5. So there are 5 threads per worker process. Okay. So in the previous slide I had explained to you all that we created a green bolt, right? So in that green bolt, how many tasks did we assign? I will again take you all to that slide. So in this green bolt I have assigned 4 tasks and I have assigned 2 executors, right? That means for one executor I am expecting 2 tasks. The same has been explained here. So for green color bolt I have 2 different executors. One is here, one is here. And I want 2 tasks to be hosted on one executor. So 1 and 2. 2 tasks in executor 1, 2 tasks in executor number 2. Right? Because number of tasks in that code example we allocated for green bolt is 4. So 1, 2, 3, 4. So 4 tasks and 2 executors. So one executor is hosting 2 tasks. Clear? On this slide I will explain to you all a simple example of how this particular topology is going to be built. So in this, just to summarize, for a blue bolt I have 2 executors. For green bolt I have 2 executors. Yellow bolt I have 6 executors. So let's go to the code. So the first step, I am creating a new configuration object, and in that configuration object I am setting the number of workers to 2. Okay, so I'll go here. We have 2 worker processes, worker process 1, worker process 2. So in this configuration I am saying please set the number of workers to 2. Then in topology builder I am setting a spout. Okay, so first spout is blue spout, right? So spout is blue color that I mentioned here. So I'm creating a blue spout. I'm instantiating a class of blue spout which is having a logic of the spout, and I am expecting parallelism to be 2. So in this diagram, for a blue spout I am having 2 parallelisms, so mention that as third parameter. Next is I am setting a green bolt. We have already discussed this code in the previous slide. I'll just repeat it here. So green bolt is an identifier for a green color bolt mentioned in this diagram. And what is the parallelism hint that we expect here? 2. So for this green bolt, parallelism is 2. How many tasks I am expecting in a green bolt? 1, 2, 3 and 4. So set the number of tasks to 4. And I am expecting shuffle grouping for this green bolt from blue spout. So green bolt is taking the input from blue spout, right? So that's why for a green bolt I am saying shuffle grouping from blue spout. I repeat, for this green bolt I am saying shuffle grouping from blue spout. So blue spout is a source of input for green bolt. Clear? So what is the next? Next is yellow bolt. Parallelism is 6 and it is accepting input data from green bolt. So third I am creating a yellow bolt. So I am instantiating a yellow bolt class. So from yellow bolt logic will be used for this bolt. I am saying I want parallelism 6. And who is the input to yellow bolt? Green bolt. So that's why shuffle grouping from green bolt. Okay, so can you understand how this chain goes? First I am creating a spout here, then I am creating a bolt here which is taking input from blue spout, and then I am creating another bolt, yellow bolt, whose input I am taking from green bolt. So there is a blue spout which emits the data to green bolt, and green bolt emits the data to yellow bolt. And finally I am submitting the topology. I am giving a name to a topology as my topology. I am passing this configuration object where I have set how many worker processes I need, and then I am invoking create topology API of topology builder. Okay, so this is how the topology gets created. So now, how to change the parallelism of a running topology? This is fascinating. So please remember that once you assign the number of tasks to a particular component, you cannot change the number of tasks associated to a component on the fly. So on a running topology, you cannot change the number of tasks associated to a component, but you can definitely change how many executors or worker processes you need. I repeat, as far as the changing of parallelism is concerned of a running topology, you cannot change the number of tasks which are associated to a component, but you can change the number of worker processes and the number of executors for a component. So in this slide, I am explaining to you all how to go about doing that. So there is a concept called rebalance. So in Storm, you can use rebalance to change the parallelism of a running topology on the fly. Okay, so in this command that I have here, Storm rebalance, I am instructing Storm to rebalance which topology? My topology. So in the previous slide, we created a topology, remember, and I had given the name to it as my topology. So I'm asking here Storm to rebalance topology whose name is my topology, and I want the number of worker processes to be 5. So when I had created this my topology, I had set number of workers to only 2, but I want it to make 5. So in this command, I am requesting Storm to rebalance my topology, and now I want number of worker processes to be 5. Similarly, the blue Spout whose parallelism was 2, I am requesting it to make it 3. And yellow bolt whose parallelism was 6, I am requesting it to make 10. So with this, you can rebalance the Storm topology on the fly by changing the number of worker processes and number of executors. So for more knowledge on Apache Storm and Kafka I have not even discussed in this very first presentation, but it's definitely coming up ahead. So to get more insights on Apache Storm and Apache Kafka, you can please email me for the remaining videos at virajonlinetutor@gmail.com. Thank you.